Next, it's section 6.4, general strategies for factoring. And yeah, the reason we care so much about factoring is we're going to need it when we're simplifying pieces of algebra and also for solving equations. So it's an important skill we'll need. And in this chapter 6, we've looked at different methods. So if you're faced with something, how do you know which method to use? So we'll look at that here. Okay, so the first thing to do is you always look for common factors. Okay, so ideally find the greatest common factor. Factor that out first. After that, then you're looking, so count the number of terms, 2 terms, 3 terms or more. And if you have a binomial, 2 terms, then yeah, really the only method we have for 2 terms is a difference of squares. So see if you can recognize a difference of squares. But yeah, most of the time we're factoring things with 3 terms, trinomials. We have the easy case. So if you just have 1x squared, then you're in the easy case, and you can just look for 2 numbers that multiply to give c and add up to give b, and those give the numbers for the factors. Another fairly easy case is the perfect squared trinomial situation. So if you see that the first term is something squared and the last term is something squared, then there's a chance it could be a perfect square trinomial looking like this. So just something squared. And yeah, so if those 2 don't work, then the last thing to look for, if it's not one of these 2, then you can try the AC method. So yeah, we'll look at another example of one of those. So yeah, this is the hardest of the 3. And if there are 4 terms, then yeah, we have a method for those, factoring by grouping. Okay, so that's our general strategy. Of course, one thing to bear in mind, not everything factors. So here's a simple polynomial, a simple trinomial that doesn't factor. So yeah, not everything can be broken down as a product. Okay, but if you're given something to factor, it should factor. Example 1. Factor completely this. Yeah, here we're saying factor completely, so that means, okay, you can factor this into a product, but make sure that each factor itself, make sure you factor each piece as much as possible. Okay, so yeah, the first step here, yeah, there is a greatest common factor. Well, again, we see all these coefficients are even, so 2 is a common factor. This is 2 times 2, this is 2 times 3, so yeah, nothing else in common to all 4. So the greatest common factor is 2. Okay, so if you factor out a 2 out of each term, then what's left? So 20xy divided by 2 is 10xy. This divided by 2, so divide each piece by 2. So this is, when you factor out the 2, you still have this factor. All right, so we've factored this thing, but there's still work to do. So yeah, it's not factored completely because this second piece can be written as products of smaller things. And yeah, this factors by grouping. And remember this method, so look at the first two, take out their greatest common factor, that's 5x. So this is 5x times 2y, this is 5x times negative 3. Then look for the greatest common factor of this the second pair. Yeah, so here there's nothing in common, so the greatest common factor is 1. Okay, but if you pull out 1, you're left with negative 2y plus 3, so that doesn't match the first factor. Okay, so the trick is to pull out negative 1. So then this is negative 1 times 2y plus 2y minus 3. So now they match, and now we can see that this is 2y minus 3 times 5x minus 1. Okay, so factoring by grouping. Don't forget the 2 we pulled out earlier, so altogether this is our answer. 2 times 5x minus 1 times 2y minus 3. And if you multiply this all out, you can check. You'll get the original polynomial. All right. Example 2. Okay, so factor this guy completely. Yeah, numbers ending in 5s or 0s have 5 as a common factor. And yeah, this is 5 times 9, 5 times negative 6, 5 times 1. So the greatest common factor is 5. Okay, so divide that out. You're left with 9c squared minus 6cd plus d squared. Okay, so this is a trinomial. We're left to factor. Okay, are we in the easy case? Is it a perfect square trinomial, or do we need the AC method? Okay, we have a 9 here. That's not a 1, so just at first glance, this is not the easy case. But 9 is a square. And also, this is a square, so yeah, so this looks like, yeah, we can use the AC method, or since these are squares, even better, let's try to match it with the perfect square trinomial template. So yeah, so here we see this is 3c squared. So that's what we're looking for. Here d, yeah, this is d squared. So is this what we have? In the middle, yeah, this is 6cd, yeah, with a minus sign. Okay, so good news, we don't need the AC method. It's we're just recognizing a perfect square trinomial with a minus sign to get that middle negative. So altogether, it's, yeah, the GCD times this perfect square. Yeah, so this, just at first glance, yeah, we couldn't use the easy method, but yeah, noting here, if you switch the order, if you put the D part first, then so rewriting it as D squared minus 6CD plus 9C squared, we can actually use the that easy trinomial case. So yes, so the D squared piece just has a 1 coefficient. So this does factor as D plus something times D plus something. Right, so 9 as a product, negative 6 as a product. Yes, so we need negative 3, negative 3, negative 3, negative 3. So it's D minus 3 times D minus 3, and include those C's to get the C's as well. Okay, so yeah, if you switch the signs here, it's the same thing because you're squaring. All right, so in fact, yeah, for this example, all 3 trinomial methods work on it. Okay, but yeah, maybe I'm confusing the issue. Yeah, I mean, for any trinomial, you can just hit it with the AC method. That'll work in every case. Example 3. Okay, so right away we see it's 2 terms. 3x k to the power 4 minus 48x. We want to factor this completely. As usual, look for the greatest common factor. So from the numbers, yeah, we have a 3 and a 48. 48 is 3 times 16. So 3 is a common factor. From the letters, yeah, they have x's in common. So the greatest common factor is 3x. Okay, so divide out 3x. So divide this by 3x, you're left with k to the power 4. Divide this by 3x, so the x's go away, you're left with negative 16. Okay, yeah, so double check, distribute, you'll get this. So we found one factor, 3x, or 3 times x, right? What's left is k to the power 4 minus 16. So from our strategy, right, we've got two terms. So is this a difference of squares? Can we write it as something squared minus something else squared? So yes, certainly 16 is 4 squared, and yet k to the power of 4 is a square. It's k squared, all squared. Okay, so k squared times k squared is, altogether you're multiplying 4k's together. Okay, so this is a nice difference of squares. And we know how to factor those. So it's the sum, so k squared plus 4 times the difference, k squared minus 4. Okay, so we're getting the sum by the difference. Okay, so we have some good factors, but we're not done yet. Remember, we want to factor this thing completely, as many factors as possible. Yeah, here we have a sum of two squares. We know those don't factor. But here we have a difference of squares again. Yes, so it's k squared minus 2 squared. So we can factor this again. K plus 2 times k minus 2. Okay, so what have we found? Yeah, we have this factor, we have this factor, and we have these factors. Okay, so altogether, this is our answer. Yeah, 3x times k squared plus 4 times k plus 2 times k minus 2. So this is, yeah, so this had a lot of factors. This is it broken down into as many factors as possible. All right. Let's look at one last example. Example 4, factor this completely. 3x to the third power this time, minus 8x squared plus 4x. For the greatest common factor, yeah, you see the numbers don't have anything in common except 1. But the letters, yeah, so they all have x's. This only has one x, so yeah, so the greatest common factor for these three terms is just x. So x is all we can pull out. Okay, so dividing this by x, we're getting, so just the powers go down, 3x squared minus 8x plus 4. And now we're looking at a trinomial. We're not in the easy case. We're not in the perfect square trinomial case either. Okay, this is a square, but this 3x squared is not something squared. Okay, so this time we're forced to try the AC method. Okay, so the AC method for this trinomial, yet a is 3, b is negative 8, c is 4. So the method says to work out AC, that's 12, b, negative 8, and we're looking for two numbers with product 12, and the same two numbers add up to negative 8. Okay, that's not obvious. Yeah, the problem is 12 has a lot of factors. You could make a table. So what are all the ways to break up 12 into a product of two numbers? 1 times 12, or negative 1 times negative 12, 2 times 6, 3 times 4. Okay, so these all give the right product, but we want those numbers to also add up to negative 8. Yeah, these two add up to 13, or negative 13, 8. Okay, perfect. These two add up to negative 8. 3 and 4 don't work. Okay, so this is what we're after. Giving the right sum, so negative 2, negative 6, negative 2, negative 6. Okay, so then we use those two numbers to split the middle term. Negative 8x turns into negative 2x minus 6x. And factor by grouping. For these two, the greatest common factor is x. So we're getting x times 3x minus 2. For these two, the greatest common factor is just 2. Okay, pulling out 2 doesn't work, but pull out negative 2, and we get these two pieces to match. Okay, so we need these two to match, so we can pull them out. So it's x minus 2 times 3x minus 2. Okay, so remembering the greatest common factor we pulled out at the beginning. So the factors are, so the completely factored version is x times x minus 2 times 3x minus 2. All right, so yeah, this one was the greatest common factor idea, just combined with the AC method. Okay, and so yeah, you can also look in the book. Yeah, the same. We're just going through this section. So here it is. Yeah, we're not looking at the cubes, but here are our. This is our strategy. And here it is spelled out. Okay, and some more examples to look at. Yeah, so do look through the book, and yeah, try the homework questions from these sections.